Hi, this is Amy, and today we're going to talk about tests of two proportions. Really, what we're going to say is the same way we develop tests of two means, we're going to do the same thing with two populations that are categorical data. Let's start with an example. In 2017, Health Canada conducted a study of tobacco use in Canada. They wanted to see if the smoking rates are different for young men and women, the difference in the proportion of men and women who smoke. I'm going to highlight that is what is of interest. A random sample of men and women aged 20 through 24 were asked if they smoke on either a daily or occasional basis. We've got a few variables going on. This is the proportion of men who smoke. P2 is going to be women who smoke. P1 hat, this is going to be our sample proportion. And same with P2 hat. So these are the things we are looking at. Just circle that. The difference between our two population proportions is P1 minus P2. I am going to take a second and note that sometimes you'll see this drawn as pi 1 minus pi 2, but we're going to use P today. Our point estimate for the difference between the two populations is really our best estimate. So basically, what we're saying is P1 hat minus P2 hat, the difference between our sample proportions, is kind of sort of similar to the real difference. So that's a real difference, and this one is the sample difference. And we're going to use one to approximate the other one the same way we normally do with hypothesis tests. There's different ways we can do this. Same as every other hypothesis test, we have lower-tailed tests. And a lower-tailed test is always going to look like this. We have an upper-tailed test. And we have a two-tailed test. They're all going to play out the same way we normally do things. I'm also going to note is that we don't have to use 0 here. That difference could be any number. But generally, the first way we do it is 0 is the most interesting. Are they the same or are they different? Not, is the difference 10% or is it not 10%? And I say between 0 and 1 because they're proportions, and you can arrange your single-tailed test to make it always positive if you try. What we're going to do is doing some pooling the same way we did before to come up with our formulas. So we have a pooled proportion, and this is just a weighted average. Weighted averages or weighted means you're going to see come up all the time. So we take all of our numbers and divide it by all of those. And this sample proportion is used in our formulas. I'm going to say formulae because that's the correct Latin for that. X1 and X2 are the number of successes, N1 and N2 are the sample sizes. And now we come up with a test statistic. This is just another formula. So we're going to come up with P1, P hat, and that is the total sample proportion. And we are going to plug it into something that is pretty similar to what our z-score normally is. We've got a standard error on the bottom, and we've got a difference on the top. And this thing is often 0, because that's the hypothesized difference that we are looking at. One thing you should be asking yourself every time you see a new hypothesis test is this appropriate? Can I do it? Are the assumptions met? We really need that the conditions that mean that we can use the central limit theorem to show that the binomial distribution is approximately the normal. Big words, but what I really mean is each group must be bigger than 5. So basically, we have X1, which is the same as N1, P hat 1, bigger than 5. So that means the number of successes in group 1 has got to be bigger than 5's. As well, the number of failures that is n1 minus x1, which is the same as n1. 1 minus p hat 1 is bigger than 5. Number of failures. And we do the same thing with group 2. For group 2, we say the number of successes is got to be bigger than 5. And the number of failures, that's n2 minus x2, the number of failures, also bigger than 5. So if those 4 groups are bigger than approximately 5, we're good to go. All of our theorems still work, and we can do this. If not, we don't have a big enough sample, and we're going to need a bigger sample. So let's get back to our example. 2017, Health Canada, etc. We're going to say men is population 1, women is population 2. And this is just arbitrary. We can choose either way to do this. So what we have is our sample proportions are 40 over 200 because we had 40 men smoked. So I'm going to write this in. Men, women, smoke, not smoke. When I draw this in here, we talked to 200 men and 200 women, and 40 of the men smoked, and 22 of the women smoked, meaning there's 62 out of 400 people smoked overall. We also have 160 and 100 and men didn't smoke, 178 women didn't smoke, and 400 minus 62 is 338 people did not smoke. Looking at this, I'm going to note all 4 groups are bigger than 5. They're much bigger than 5. That means in this case, we are good to go. We have a big enough population. So we can proceed with our hypothesis test. Here, the only difference in the hypothesis test is going to be in that test statistic. Once we do that, everything's going to go the exact same way it normally does. So here we have 40 over 200 men, 0.2, 22 over 200 women, 0.11. I'm going to note it's okay to round. Sorry, it's not okay to round. It's okay to put in decimal form if there's no rounding. If there is rounding, just leave it as a fraction. It's only one population there we're looking at. This is our p hat is 62 over 400 or 0.155. Our hypothesis tests, I'm going to put this here. There is no difference. The alternative is there is a difference. And I'm going to note, if we wanted this to be a one-sided test, we could say something like men smoke at a higher rate than women. That's a one-sided test. But here we're going to do a two-sided. So we've got this. We've got our hypothesis. Our alpha is almost always 5%. We are looking at a Z distribution because it's a proportion, which means that our critical value is plus or minus 1.96. I like to put that in here. Put in our critical values and shade. So we're going to reject H naught if Z test is less than negative 1.96 or Z test is bigger than 1.96 if it's in that rejection region. Now, we just dump everything into this long equation. I'm going to scroll a little so I can write everything. Z test is P1, which is men, 0.2 minus 0.11 minus 0 over this giant standard error that hangs out in the bottom. Our big p hat was 0.155, 15.5%. And then we multiply it by this thing, 1 over 200 plus 1 over 200. It's worth noting that in this case, our sample sizes are the same, but they don't need to be. Okay, what do we get from this? Trust me that I've run this through a computer and it's 2.49 rounded. So we draw that in. And what is our conclusion? We're going to reject I'm going to scroll up, and we say at the 5% significance level, there is enough evidence to show that there is a difference in the rates at which young men and women smoke. Now what I'm going to do is find that p-value. If I draw over here, we can see that the area to the right of 2.49 is 0.0064. And because it's a two-sided test, I'm going to add that in again, which means I get a p-value of 1.2%. Let me get this correct, 0.129 when we actually run it through a computer and round it properly. That's what our p-value is.